Turbulent flows are essentially all around us in the atmosphere through rivers, brooks, uh, clouds. I have focused in my own research on how turbulent flows impact mechanical and aerospace systems. In particular, my interests lie in the aerospace sector. We focus on high-speed jets in our facility at Skytop. We have our anechoic chamber where we are looking at methodologies for reducing high-speed jet noise. For example, the noise around airports when the jet is taking off. We have ideas on how we can reduce that noise. That would be on the commercial side. We also are working with funding from the United States Air Force. And there we are looking at military applications of jet noise reduction as well. This is very important for neighborhoods around Air Force bases as well as for naval applications, including aircraft carriers, where our personnel, our Navy personnel, are exposed to extremely high levels of noise, and this is becoming a critical issue for us within the U.S. military. And so, again, we're working both the commercial side that we all deal with on a daily basis, as well as the military side of the noise problem. The anechoic chamber, which is our large-scale facility at Skytop. Now, this facility was actually built by a Professor Dosanjhi, who was here for many, many years. This facility was built in the 70s and had been basically vacant, frankly, for several years until I joined the faculty here at Syracuse University. We brought this facility up to modern conditions by improving the instrumentation. We essentially spent a great deal of funds to get a new jet facility actually in the anechoic chamber itself. So maybe just a couple comments on what do I mean by anechoic, because I think that's pretty important. If you're at an airport or on an aircraft carrier and you have a jet taking off, so imagine you have sound waves emanating from that jet. When you're at the airport and you're taking off, those waves can more or less go to infinity, and so you don't get reflections. How do you do those similar kinds of experiments in a laboratory? Imagine that you would try to do this without some sort of sound absorbing material. So if in this room that we're sitting in now, I can go, whoa, and you can hear the reflections, the echo. We don't want that in our studies. We want to mimic the same conditions that we have at an airport or on an aircraft carrier when the jet is taking off. We want to mimic those same conditions. So we have to use what we call an anechoic facility, which is a facility where we have large wedges that are in there that absorb the sound so that we can essentially have the same physics, if you will, in a laboratory that you would have in the real system. It's difficult to do careful experiments in the real systems, though, so we need to be able to do those in the laboratory.
I'm a PhD candidate here at Syracuse University, and I actually did my undergraduate degree here at Syracuse. I got my BS in Aerospace Engineering in 2009. I got my Master's in Mechanical and Aerospace Engineering in 2011, and I hope to finish my PhD in Mechanical Aerospace Engineering in 2014. Now entering our anechoic chamber here at Syracuse University. There are very few anechoic chambers at academic institutions in the United States, and this is one of the bigger ones actually. So if we take a step in here, so you'll notice that the entire chamber is floor to ceiling covered with fiberglass wedges. These wedges are fully anechoic, meaning it absorbs all the sound, so there's no echo inside of the chamber itself. And this allows us to take our jet measurements. So if you look over here, we have a fully compressible turbulent jet. We have 5 compressed air tanks that we compress up to 400 psi over in our other facility. Once these tanks are fully charged, we can get upwards of Mach 1 flow coming out of the jet nozzle. So what we do here is we measure the jet noise to try and reduce it for military and also commercial applications. So in this current configuration, we have far field microphones which measure the acoustic pressure, and in the near region of the jet we have these small pressure transducers which measure the hydrodynamic pressure. In addition, we have a laser, which you can see here, and cameras so that we can illuminate the flow field and take pictures of it. So we can not only look at the velocity of the flow, but then we can also get pressure, sound information, and using all those things we can hope to reduce jet noise for both, again, military and commercial applications. And this facility, again, is very rare to see one of this size at an academic institution, so we're very lucky to be able to work in this chamber here.
We're also working on improving maneuverability of aerospace vehicles. Different types of applications might include enhancing the maneuverability of unmanned systems. A lot of our research can impact that. And we're also looking at bringing these concepts that we've developed primarily with support from the Department of Defense into the energy sector. We are a member of the University of Minnesota Wind Energy Consortium. Here at Syracuse University, we're looking at bringing our closed-loop flow control tools that we've developed with DoD support to see if we can't, number one, improve the efficiency of wind turbine systems. We're talking large-scale wind now, as well as seeing if we can reduce the noise that such systems may create through, again, intelligent systems and control concepts.
I'm a first-year grad student here at Syracuse University in the Mechanical and Aerospace Engineering program. I did my bachelor's here as well in Aerospace Engineering. This is our subsonic closed return wind tunnel we have in the sub-basement of Link at Syracuse University. Subsonic meaning below Mach 1, so below the speed of sound, so slower speeds. It's a 3-foot by 3-foot test section, and closed return means that there's a fan that circulates air and it goes around, and the same air is recycled over and over again. What we can do here is we can put things on a sting, which is attached to a force balance below. So we can put things like this airfoil on the force balance, and we can measure the drag, lift, and moments of the wing or whatever we need to do.
We've had many undergraduates come through the lab. This has been a key source of great help for us. You have really talented undergraduates here at Syracuse University in our engineering and computer science school. In particular, in my case, I would be interfacing primarily with those in mechanical and aerospace engineering. And those students are able to come into the lab throughout the semesters. We call this research experience for undergraduates. This is something that we as a university, we as a college within Syracuse University really value very much. And it's a great way for kids to make decisions as to whether they want to go work in industry or maybe they want to go to graduate school. And that's an interesting decision. A very famous engineer named Theodore von Karman, who was at Caltech, basically he had a great line. He said, "Scientists study things which are, engineers create things that have never been." So it's a fascinating space of creativity and building on strong fundamentals in the sciences, but then being able to take that and package that and use that information to develop new things.